This is about joint work with Anton Mallasto and Stefan Sommer. I just want to start by giving some motivation for this. So what we really want is to derive methods to simulate bridge processes on general Riemannian manifolds. And this picture should kind of illustrate, I guess should illustrate how that would look like in here on the sphere. This is kind of cheating because these are just standard Brownian bridges in two-dimensional Euclidean space where we've used stereographic projection. So the problem here is like the processes cannot cross the cut locus. So instead we turn to the case of the flat torus just to remove some of the geometric properties, like there's no curvature, so this has to, in the case of flat torus, it has to the Euclidean topology, but it still has the problem of crossing the cut locus. So the first picture here on the right is how two bridge processes would look like on the torus, where the blue point is our starting point, and then we condition on the cut locus, which is the red point here, and the right image is how you should actually interpret it in two-dimensional space. So you have the two spaces paths here, starting at, so the dotted line here is the cut locus, and then you have the torus is this case, and this is just the lift to the Euclidean case. So we consider a canonical projection from the two-dimensional Euclidean space onto the torus obtained as the quotient manifold of R2 modulo Z2. And in this case, then two-dimensional Brownian motion is just projected onto a Brownian motion on the flat torus. And the intuition here is that if we condition the Brownian motion on the torus by some point, then we would get a Brownian bridge on the flat torus here. We condition on a point B, that is the red point here, and then if we consider the pre-image B, so the pre-image Z, then we get these points in Euclidean space. And then if we lift the process to Euclidean space, we would condition the process, the Brownian motion in R2, to end up in this pre-image set. So as you see here, like there's this grid line. This grid indicates the cut locus of the flat torus, and that's kind of where we don't have a unique minimizing distance to any of these points. Right. So first, let me just briefly review the Euclidean case. So we have this diffusion process X, and we're conditioning it on hitting a point in Euclidean space at time capital T. The distribution of this process, the conditional process of X, is the same as that of another distribution, diffusion, Y, where it has the same diffusion term, but the drift term has now an added term in terms of the gradient of the logarithmic heat kernel. And in the case of drift B here being 0 and the diffusion coefficient being 1, then X is just the standard Brownian motion, and then Y restricts to the standard Brownian bridge, just having the drift as the gradient of the logarithmic heat kernel. So on the flat torus, since it is flat and it has the Euclidean structure, you can actually, we actually have a closed form expression for the heat kernel. So that is actually what we have at the denominator here. This is the lift to R2 of the heat kernel on the flat torus, and by means of Dup's H transform, you take this function H. This provides that it's martingale, so we can use this Dup's transform, and then we get a conditional SDE, which is the lift of the Brownian bridge on the flat torus to the Euclidean space, where the drift term is now summed over all points in the pre-image set, and G here is just a normalizing constant, and then this term here is a vector pointing to each of the points in this conditioning set here, and it is scaled by t, so we kind of get a stronger drift as times moves on. So our intuition was, okay, we want to do it in cases where we don't know the transmission density when it's intractable. So this is just to review a result of Brownian, who says that on a compact sets away from the cut locus, we have uniform convergence of the logarithmic Higgs kernel in this sense here towards the squared distance function. And similarly, it holds for all the mth covariant derivatives of this. We have the same kind of convergence. And then we wanted to use the term on the right here as our drift term. So that led us to this SDE. So once again, just say, in this case of the flat torus, you can actually simulate pretty well you can actually simulate the true Brownian bridge. And instead, we chose to look at this diffusion process where the drift term here just directs to the closest point in the conditioning set. So that gives us so here you have the indicator function removing the drift whenever the process is at the cut locus. So we get this discontinuity of the drift, and then we ask if there exists a strong solution to this. And just to give you an idea of how it looks like, so the left image here is a sampled process from the proposed diffusion, and added are vectors of the drift term guiding to the closest point. So you see, as time goes by, the drift becomes stronger towards the conditional point. And on the right side, we have like the underlying vector field structure of this. So to ensure the existence of a strong solution, like typical assumptions are that the drift and the coefficient needs to satisfy some global or local Lipschitz properties, and clearly we don't have that. But Veritenikov kind of showed that even in this case we have a strong solution of our SDE. So that means that our process is actually adapted to the filtration generated by the Brownian motion, which is rather nice. So this is just on the left here. We have sample paths from the proposed diffusion, and on the right we have 9 sample paths from the true Brownian bridge. And as you may see, like in 1 in 3 cases, they don't converge to the same point, and that kind of illustrates that if you look at the bottom right picture here, that at time close to time capital T, then the drift becomes so strong that it cannot kind of cross cut locus, whereas the true distribution still have pull in all directions here. Oh yeah. But it looks from the images as if the proposed diffusion actually converges. So is that the case? Well, first we have this heuristic argument that kind of states that for all sample paths that kind of stays within the cut locus on some small time interval before the end time. Then we have almost sure convergence. But this is, as I said, very heuristic, because we need to ensure, like, to make this formalistic, we need to ensure that the process at some point stays within these open sets with probability 1. But that actually do hold. So when considering the diffusion on the torus itself, then we actually get that the diffusion converges almost surely to the point on the torus, which was proved by James Thomson. And that means that we can set the endpoint equal to our conditioning point and extend our process to a continuous process on the whole closed interval, which then entails that our process in R2 will be in this conditioning preimage set. So the next question is, do we have absolute continuity of the laws? So before I continue, just briefly reviewing this. So P of A is the distribution of our Brownian motion, and P A B T is the law of the Brownian bridge. Then we have absolute continuity of these two measures. Of course, they become singular at time capital T because the probability of a Brownian motion taking one specific value is 0, whereas under the law of the Brownian bridge it has probability 1 of happening. But this density depends on the gradient of the logarithmic heat kernel, and this term actually, by Gesano's theorem, says that under pseudo-local change of measure, then we can relate these two. So if we just consider the SDE, like the true Brownian bridge SDE, this is on the torus. As mentioned before, then you have the drift depending on the gradient of the logarithmic heat kernel. Then expressing our proposed diffusion on the torus through this true Brownian bridge by adding this extra drift term, which is just removing the drift in the Brownian bridge and then adding the drift that we want. So here it's gradient of the distance function, or squared distance function. So this f function is actually bounded away from t, and similar from Valratan's theorem result, it actually converges to 0 as time goes to capital T on all compact sets array from Cotlogos. So this entails that this process L of t is a true martingale, and that means that we can define, like we have absolute continuity, we can define a new method as Q AB of t, which will be the law of the proposed diffusion, and it will be defined through this Radon-Euclidean derivative here. So yeah, they kind of relate to each other. So next, so just to conclude here, we show that the proposed diffusion actually satisfied the bridge property, and that it will be absolutely continuous with respect to the true Brownian bridge. So the next question could be, does the diffusion actually satisfy some time reversal property? Yeah, and then for the future work, we want to use these things to analyze protein structures. So yeah, that's kind of it. Just some few references here. But thank you.